All right, so we're on to the second part of chapter 6, which is we're going to transform and combine random variables. So last lesson was all about what are random variables. Now we're going to transform them, multiply and add things to them. Okay, first up is definitions. So if you add or subtract a constant to each observation. So this is like when we were back in the first unit, pretty sure first or second unit, we were talking about if you add or subtract or multiply or divide numbers, how does it impact the mean and the standard deviation? So these are the same rules from then, right? So if you add or subtract a constant a to each observation, right, it adds a to measures of center. So that would be like your mean, your median, your quartiles, right? Your percentiles. I'm just gonna leave it like that, quartiles. Um, but it doesn't, maybe you don't remember this, but it does not change the shape or the spread. The spread is still the same. So those impact things like the range, IQR, and standard deviation. Those are not impacted. If you multiply or divide by a constant, yeah, I don't know if we have 4. I think we have 3 dots, so we'll just do 3 here. So it multiplies or divides the measures of center. So it impacts those same things, right? Mean, median, quartiles. And this also impacts the spread, right? So this multiplies or divides the measures of spread. So range, IQR, SD. And remember, it's just by the absolute value of, it's positive only. So let's just write that. It's a positive only. The negative doesn't matter. But shape does not change. So the only thing, shape never changes. And then you have to remember when you're adding or subtracting, it only impacts measures of center. When you're multiplying or dividing, it's impacting measures of center as well as measures of spread. So we're going to use that throughout. Okay, first example, El Dorado Community College considers a student to be full-time if he or she is taking between 12 and 18 credits. The number of units or credits, X, that a randomly selected EDCC full-time student is taking in the fall semester has the following distributions. There's a probability distribution, and there's a histogram of the probability distribution. So they have told us we can calculate, but I'm going to tell you this mu x is 14.65 and sigma x is 2.06, right? So you could do that by putting this in your calculator and running the 1-bar stats. But I'm just going to give us those now, save some time, okay? Now, if I go, so what does this mean? That means on average, they're taking 14.65 units or credits in the fall semester. So the next one says at EDCC, the tuition for full-time students is $50 per unit. It's pretty cheap, right? If tuition T for a randomly selected full-time student, then what does this one say? Oh, then so the formula, they want us to put the formula. So basically to find the tuition, I would take $50 and multiply it by how many credits they have, right? 50x. So here is the probability distribution for T, the tuition, and then the histogram, okay? Again, you could type those in your calculator to find mu and sigma, but I'm going to tell you it ends up being 732.50 for the mu, and sigma ends up being $103, okay? So let's look at how that changed from before. If you look at the 14.65 times 50, right? See if I can share this one, yeah. Let's go to A. So 14.65 times 60, that gives us, oops, not 60, times 50. 14.65 times 50 is $730.50, which is what we got, right? And if we also take 50 and multiply it by the sigma, we're going to get 103. So let me switch back. That was just to show to you guys. This one. that the mu and the new sigma are impacted by multiplying each of the former ones by 50. So what can we write? What happened to the shape? There's no change, right? If you look at the shape of this histogram up above and the one that's multiplied by 50 to find the tuition, the shape is exactly the same. But I'm going to use a pen so I can write mu of t, right? So our new mean is 50 times the original mean. And our new sigma of the tuition is also 50 times the original sigma, right? So that's just a proof of the rule we had at the top. So now let's keep going. This is what we said at the top. Okay, so I'm not going to read that one. So now let's go to this next example. In addition to tuition charges, each full-time student at EDCC is assessed student fees of $100 per semester. So everyone pays an extra $100 for student fees. So if C, the overall cost for a randomly selected full-time student, it would be, you would take your tuition, right? And then you would add $100. So your tuition, add that $100 fee. So now let's keep it moving. Here is the probability distribution for cost. There is the histogram, and you can type all that in to your calculator, but you will find that the new mu is 32.5 and the new sigma is 103. Okay, so let's look how that changed. 103. 103, no change, right? So the sigma had no change. And then, oh, this I forgot an 832.50. And then how did our mean change? Well, it's 832.50 before it was 732.50. So just like we talked about above, we can say what happened to the mean? It increased by $100. What happened to the standard deviation? No change, which is what we talked about above. What about the shape? So if I look at the shape of this graph compared to the former two, the shape is exactly the same. So shapes are the same. So this is a summary of what we wrote on page 1. You can read through that. Here is a check your understanding. You want to pause it. I'll put the solutions up and you can check that. Okay. Now, let's talk about linear transformation. So this is kind of just putting all the things we talked up on the last page into a formula. Okay. So so it says if y equals a plus b times x, which is a formula we're all familiar with right now, right? So that's a linear transformation of the random variable x. You're multiplying by b and then you're adding a. Then the probability distribution of y has the same shape as the probability distribution of x, right? There is no change in the shape. That up. And then we can say mu of y. Well, how does the mean change? You have to add that transformation as well as multiply, right? But we know the sigma is not impacted by the addition or subtraction. So that one, you just take the absolute value of your multiplication factor, because remember, we're not going to make it negative, and you multiply it by sigma x. So that's just putting some notation on what we did in the last two examples. Trying to get the sun out of there. Okay. New problem. In a large introductory statistics class, the distribution of raw scores on a test, so X, was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. The professor decides to scale the scores by multiplying the raw scores by 4. So we're going to multiply by 4 and add 10. So our B is 4, our A is 10. Define the random variable Y to be the scaled score of a randomly selected student from the class. Find the mean and standard deviation of Y. So our new variable Y is going to be taking that 10 extra points and then multiplying each score by 4, right? So there's our formula from up here, y equals a times bx, okay? And then now we need to find the mean and standard deviation. So I'm going to write mu of y equals, I'm going to type this so I can go a little faster, right? it's going to be 10 plus 4. Gotta write this one times the mu of x. Okay. Okay, so then we're like, all right, what is the mu of x? Well, it's up here, it's 17.2. So I need to figure out what is 10 plus 4 times 17.2. That just ends up being, I have it in here, 78.8. Okay. So the new mean score with those adjustments is 78.8 points. And then it also wants us to find the standard deviation. So I'll do that over here. So I'm going to write sigma of y using this formula right here is just going to be the scale factor, right? The thing we're multiplying by. So 4 times sigma x. So that's going to be 4 times, what's our sigma? 3.8. Standard deviation is 3.8. So when you work that out, sorry for my sloppy handwriting, it ends up being 15.2. Okay. So my new standard deviation with those adjustments on the score is 15.2. So now we need to use that normal distribution thing. It says, what is the probability that a randomly selected student has a scaled test score of at least 90? So we know it's normally distributed. We know our new mean is 78.8. We know the standard deviation is 15.2, and we want to find above 90. So let's just make, so if that's 78.8, let's say that's 90. We're looking for this area, right? And remember, when you're doing this FRQ, you need to either write this in words. I am finding the area above 90 for a normally distributed curve with a mean of this and a standard deviation of that. Or you can label, right? We're finding this area. That's my plan. So how do you find that area? We need to find, I'm also going to say, we're finding the probability that y is greater than or equal to 90. So I've drawn my picture. I've written my statement. I would probably put under here, like if a real FRQ, I would copy this down again. Sigma y equals mu x, mu y equals. So I have all that laid out. And then you're going to go to calculator. So let's share a different screen. And then remember, we go to probability, distributions, normal CDF. Yes. So we want from 90 to infinity. So remember, you have to go to, I think it's control book. Donna taught me that one, to infinity. My mean is 78.8. My standard deviation is 15.2. Okay, so it is 0.2306. So let's switch. Zero point 2306. Okay, so the probability of a randomly selected student having a score of 90 or above is about 23%. Okay, so now we're kind of putting all those things together from the first unit to this one. Let's keep it moving. And now we're going back to that community college example. EDCC also has a campus downtown specializing in just a few fields of study. Full-time students at the downtown campus take only 3 unit classes. Let Y equal the number of units taken in the fall semester by a randomly selected full-time student at the downtown campus. Here's the probability distribution of Y. So the probability of someone having 12 credits is 0.3, 15 credits is 0.4. They've given us the mean and standard deviation. The question is, if you were to randomly select one full-time student from the main campus and one full-time student from the downtown campus and add their number of units, the expected value of the sum would be, we're out of space. So it would be, I'm going to write it up here. You can squeeze it somewhere. So the expected value or the mean of the sum, right? If you're adding from the 2 campuses, would literally be mu x plus mu y. You just add the expected values or the means. Okay. So you can squeeze that in there. And that's what goes here too. Oh, maybe that's why there's no space. You're supposed to write it here. Mu x plus mu y. Okay. So you have to combine the means, just add them. In general, the mean of the sum of several random variables is the sum of their means. It's the sum. Easy enough. Okay. So there's a definition here. If knowing whether any event involving X alone has occurred tells us nothing about the occurrence of any other event involving Y alone and vice versa, then they are independent random variables, right? So in this case, the number of credits someone takes at their downtown campus has no impact on the number of credits some other student takes at their main campus. They are independent random variables, okay? So probability models often assume independence when the random variables describe outcomes that appear unrelated to each other. You should always ask whether the assumption of independence is reasonable. So you're always thinking about that. If it's not, you want to state it.